Yes. Yes. Yeah. So in the if you are in D greater than 4 dimensions, and then if you look at the, so as we were remember discussing that in D greater than 4 you don't have these logs. So 1 by omega to the 0 and omega, and the omega term will start seeing the B field, and we have that effect has been considered.
That's for the gravity and radiation, but what about just the beam?
Oh, you mean just the field, the radiation itself? Yeah, that I am not aware if someone has looked at the B radiation. Yeah.
Similarly, same questions for this P-forms.
For the radiation of P-form field, that also I don't think anyone has looked.
And then you put this for the P-forms also.
That has been considered. Yeah. This is Ashok's proof of take a generic, generic gravitating spectrum, and then you look at soft factorization. So in D greater than 4 dimension for gravitational radiation and electromagnetic radiation, we know what is the effect of the other contribution other fields are, but all other fields.
And just to clarify that point, so you won't be able to distinguish a beaming field from spin zero field of the same. I mean, if you make the
No. So that's what. So if you go to the order, if you go to the subs, what we call sub-leading omega order, you would distinguish. Yes. But that's in D greater than 4 dimension. So in D equal to 4, all bets are off because of these log issues. Okay, so I'll just Chetan is also there. So I will just tell you where we are in our discussion, and then what we want to do for the remaining part. So far we only look at classical gravitational scattering, and we derived this result really in D equal to 4 dimensions. I'm not rewriting the proof in the statement in D greater than 4 dimension, but we saw that there are these two objects which depend on the only the external momenta of the scattering objects, and they are of course parameterized by the angle at which the detector is placed, and these are completely theory independent, right? So that was the thing that we have seen so far. So we are really at this. So this universality just refers to the fact that these two quantities can be completely fixed once we have the asymptotics of the gravitating states completely determined. Even we don't even need the spins of the particles, we only need the momenta. And so these two are observables in their own right because they are part of radiation, right? So they are, even though we are in a theory which has general covariance, these things are, because they are computed at infinity, they are basically gauge invariant, and so these quantities are called event shapes. So we have these two observables in gravitational scattering which are universal, completely universal. And so today what I want to do is to sort of try to at least discuss what's the really the origin of this universality, which comes from this structure of symmetry in classical gravitational scattering. And then basically tomorrow and Friday we will do we will see the impact of all this on the quantum S matrix in gravity. So that's roughly the roadmap that we will follow. So just yeah. Yeah, this is just this is your theorem, but this is just a classical part right now. At this stage, sorry, you are asking something else?
I'm asking about this relation between.
Right now it will be. We will first do classical, and then we will see if we can quantize and get some word identity for the S matrix, and if those explain for us what we call factorization theorems in quantum gravity. So right now today's lecture will be completely again classical. Okay, but you shouldn't curse me because you said that the following lectures are memory and all, so that's why I'm focusing more on the classical. so this E mu nu, I will not write the formula, but if you want me to recap, please ask. Or maybe I will just schematically write because Chetan is also here. That it has two contributions, one coming from the matter and one coming from the finite energy gravitational radiation, as we saw. And very quickly to write, schematically this is some or all matter particles incoming and outgoing. And this one is the same thing where you, so because we discussed this, I'm just writing the formula, but please ask if it's not clear. We look at the linear momentum of the radiation itself, and that contributes This was the, so this is really called in the general relativity literature linear memory, linear displacement memory. I will tell you why displacement in a minute. And this is called the nonlinear displacement. And this this is nonlinear because it's nonlinear in the gravitational field, whereas this one just came from solving linearized part of the Einstein's equation, because the only contribution came from the matter stress tensor. So that is the reason for calling linear versus nonlinear. And the name displacement comes from the following fact, that if I just look at this expansion now, then you see that if I want to isolate the first mode, which is this E minus 1, then what I do is because all the other terms will drop, and so this is so this will sorry, and this is precisely, so it's like a static mode of the gravitational field. And the fact that it is a static mode means that it is this is something we will not discuss in any great detail, but what you can show is that if you, the physical interpretation of this, I will give you a reference, which is Braginski and Thorne. And the physical interpretation of this, which is in this beautiful paper, is that if you consider two particles and some gravitational wave comes and hits these two particles, then the particles will oscillate, because the wave basically induces oscillatory motion on this particle. But you wait long enough after this peak of the wave has passed, and then of course the particles will stop oscillating, but they will return to a position which is not the same as the initial position they started with. And that difference between the initial separation and the final separation is completely fixed by this mode, and that's the reason it's called displacement memory. So that's the
E mu nu is, how is it related to H mu nu? I mean,
it's just it's just our yes.
So if the particles are separated, why should the necessary oscillate? Why not just collapse?
No, because we are saying that okay, they are far away from they are very like infinity. It's like they're part of a detector. So it's like our LIGO detector, right, where the things are clearly oscillating. But the point is that even in LIGO detector, and that's why people are expecting that if the advanced LIGO or LISA, one will be able to measure even the displacement memory, and that's why you see that there is a lot of literature in post-Newtonian waveform modeling which deals precisely with these memory terms, which I think the next speaker will talk about.
Also, the mirrors are going to be in the same position after displacement.
They will not be in the same position. They'll be in the new position, and that new position is and Braginski and Thorne in their paper basically claimed that because this is like a very large distance effect, they just claimed that there can be no contribution in this effect from the gravitational field itself. And so then there was a paper by, this is an interesting anecdote by Christodoulou, which is impenetrable if you read it. So what the formula in the end he found was that their claim was wrong, and using some rigorous GR he showed that there is actually a contribution like this, which is also going to contribute to this displacement memory. And after that Thorne and Braginski wrote another paper saying that it was, I think that's an interesting quote in the paper by Thorne, that it was humbling for a physicist to see that rigorous math can actually correct some physics. And then he gave a intuitive explanation for this. So if you look at Christodoulou's paper, it's not even clear what this it's all in terms of some geometry, some Newman-Penrose formalism, something. But then Thorne clarified that this is just the linear momentum of the gravitational field. So it was an interesting discussion there. So anyway, so that's the E minus 1, and so this is one observable. This is what we call the first event shape. And we call it event shape because it's a function of the sphere, so it's not some. Should I keep this open or? Yeah.
That cannot happen at all orders, right?
Say that again.
So the fact that you're able to separate out E mu as something coming from matter and something that is coming from gravity.
Yeah.
This separation is not possible at all orders.
All orders in.
Higher orders in.
No. Exactly. So as we saw that this one, and this is what Justin also asked yesterday, this has no contribution from the gravitational field itself. Like this has no contribution. This only has contribution from the matter particles or the matter sources.
But at higher orders, I would imagine that you won't be able to do this separation even if there is no contribution from gravity.
So the in the you mean okay? So if you go to omega to the 0 order, like the next order, suppose if you computed this for a given scattering, this still has this split.
But how is that possible? So if I have a coupling of the matter sector with gravity, so for example, R mu rho lambda.
Yeah, so that coupling is influencing the final momenta, right? So you remember the setup here is that this is not right. So this is not a perturbative result because we are saying that we are given some initial momenta and final momenta. So that coupling, which is influencing the evolution of the objects themselves, that is all part of the final momenta determination in terms of initial momenta. Right? This is the contribution of the finite energy radiation to the soft radiation. So that's why there is a split. So there is no because this everything is order. I didn't write it because it's it just came from our analysis directly, but it's an exact formula in Newton coupling expansion. Okay, and now this E log, just to I will not write it because it was a long formula that we saw yesterday. But just to recall, it's also completely fixed by, I will write it schematically, pairs of particles and some function which we wrote down for yesterday in the lecture. So where again this quantity is only determined by the momenta of the particles, and this is some long expression. Okay, so now the point is that this is clearly something interesting in the sense that if only thing we know, I mean the whole point of this event shapes is that you are given initial and final configurations, then you are able to write down the formula. And how can it be that some of these things don't depend on the details of the theory? So the simplest examples of this is just conservation of momentum, right? So there we know that final momentum is equal to initial momentum, but that is true independent of the details of a scattering because of the global symmetry of our theory. And so the fact that the final radiation is completely fixed in terms of some final momenta and initial momenta, it tells you that there may be some conservation law associated to both of these event shapes. And so that's the point that I want to discuss now. And that so if there is any question. Okay, so now we will just switch gears a little bit, because to understand these conservation laws we have to understand the structure of our space-times a little bit more. So the first thing we should realize is that everything here is at the boundary. So this is a field at the boundary which is determined by the initial momenta which are at t equal to minus infinity, final momenta at t equal to plus infinity, and this radiation, finite energy radiation, which is also at the boundary. So this whole equation is everything in terms of what we would call like a boundary data. So even if to understand, if we want to discover some deeper reason behind this universality, we should look at the boundaries of our space-time more seriously. So that's what I will first do, give you some small discussion of what's the structure of a boundary of a space-time when we solve Einstein's equation with zero cosmological constant. So yeah.
I don't want to read it.
No.
So
Yes, yes, absolutely.
This does not do that, right?
No, we have not done that. And the point is that that as we discussed that even if we take this as a scattering happening in a small patch of de Sitter, we already see some interesting differences from this this result. So you are right that. And one of the reasons why we are not able to say definitively once we have de Sitter is because of what I am going to discuss now. Because this is everything is really determined in terms of the boundary, and boundary structure of ADS and DS is qualitatively different than that of flat space.
Can I just clarify? So these two terms that have this universal feature,
Yeah.
that you can actually verify with LIGO or some measurement or something.
Yeah. So I mean that's the hope. Not LIGO is two because there are two. This is because we are doing a soft expansion. It's a very low frequency. So it's a very low frequency effect, and so the signal to noise ratio has to be very good in a detector. So there are proposals in LIGO community that this term will be for some mergers, for example, of supermassive black holes. What is the sensitivity you need of a detector to actually measure this displacement memory?
And when they do these calculations, do they take into account this cosmological redshift?
No, this modeling do not. They are this form. They are exactly this formula.
So,
Yeah.
so the statement is that in LIGO this is not measured. Is that correct?
So far, no. It's not measured.
And I think that because of the colliding black holes are like let's say order of, roughly the order of the age of the universe.
Yeah.
I think lambda might play a role, right?
Yeah, it may be. Oh no, absolutely. I am completely with you. If the inspiral was in early universe, then the memory would be influenced by the presence of lambda.
I thought the Z is roughly around 1.
Yeah.
It's colliding black holes, whereas the background radiation is like Z is like 1,000.
Background radiation is, I think that's true, but I think is that but are we getting errors because of CMP? I thought
No, I think that is not true.
No.
I think that is true.
I think one thing is that I've heard is that the waveforms in the inspiral etc. are actually they don't take into account this at all.
No, they don't.
I don't think it matters probably because that's a very short term.
Yes,
right?
yes.
Because inspiral time.
Yes. So
But
for
I think that
yes.
when you're comparing it against across time scales, it might be.
Yeah. But I think I should say also one more thing that somehow this is a different discussion in its own right. I will just tell you some surprises if you try to do if you compare this formula with the formula that people write down in the post-Newtonian community, and the worst qualitative difference comes because in the post-Newtonian computations we are interested in the bound state problem. So we have an inspiral, and so what people study, and this is some detailed calculation by Favata, and what he shows is the following that, and maybe I'll spend few minutes because this is really a puzzle, an interesting puzzle, which is that if you start with some inspiral, and post-Newtonian means we can't really trace the dynamics of this beyond some point where the merger, when they come too close. So there is something called coalescence time. So basically the intuition is that at some point when the speeds become too high, then you forget about the post-Newtonian approximation, and this time, let's say this time is some in the retarded parameter some UC. So now the computation that people do for displacement memory in the post-Newtonian is really to look at the radiation coming out of this region and then look at it in the low frequency limit. Now when you do that computation, which Favata has done, he sees that so here you see that if there's an overall G, but clearly this term is higher order G than this term, right? Because this is quadratic in h mu nu, right? So this is like G square order higher than that term, because h mu nu goes as square root G, so this is G square order higher. But when Favata does this computation, he shows that for quasi-circular orbits, this one occurs at a lower post-Newtonian order than this one. But in the inspiral problem, V by C expansion and G expansion are related. So this seems completely crazy that why is it that clearly the nonlinear memory, which in a scattering problem clearly occurs at higher order in G because it's a nonlinear effect, how is it that it is occurring at a lower order in the post-Newtonian computation? And this is something that we did with Anthony. Unfortunately, we haven't published yet, which is that Guillaume Fay, where we have seen that really the subtlety lies in the fact that all the computations are for quasi-circular orbits. And it's a remarkable thing that if you look at the elliptical, general elliptical orbits, then there is really a qualitatively new contribution in the linear memory which comes at leading order in the post-Newtonian expansion. But it's not, we haven't checked everything, so I'm telling you a result which may not be completely correct. But so take it as at least as a puzzle, that there is a puzzle that in the comparison of this formula for hyperbolic scattering with the formula people write down for bound state, and we think that the solution to the puzzle lies in the difference between quasi-circularity and elliptic orbit. But
So circularity is a fine tuning.
yeah, that's what it seemed like from our computations. But we have, it may be wrong. So let me say that's a puzzle that I think it may be good. Maybe the next speaker may be able to shed some light on this issue. But we spoke to many people like Ajit and Arun and all, and they also because they were also puzzled, because for them this term is always at a lower order than this one, and they never thought in terms of hyperbolic scattering and this formula. So it was really a puzzle in the post-Newtonian community. It's still a puzzle, I should say. Yeah. Okay. Now let me just, because Chetan asked something, let me write one more formula, which is that everything we are writing here, and this formula will be a bit eliminating. So everything we are writing here is in frequency space, but you can write now, you can go back to the time domain. And then something very interesting happens. So if you go to so remember the Fourier transform we did was from omega to u being the retarded time. And so if you just do Fourier transform of this, because we are doing an expansion at low omega, the contribution happens at large u. And so this, all the details of this careful Fourier transforms can be found in the paper of S Cube. They have an entire section on this early low frequency late time Fourier transforms, even for higher order. I think you guys do even some log omega square Fourier or something. So it's a good dictionary to have. And what they show is that this term, when you Fourier transform, looks like, so let me write first as u going to plus infinity, because small omega means you can go to plus or minus infinity. So we have to evaluate both the limits differently. If you let me first look at plus infinity, then you get I will explain what this out means. And if you go to, I will explain this extra label in a minute. And if you go to minus infinity, then it is so dot is because these terms have suppressed, of course. So the statement is that, and this is what we called tail to the memory, because of the fact that you see what is happening is that as you go into infinity, this term sort of decays and you build towards this term, which is the displacement memory. So this is the tail and this is the displacement memory. And both of these have been investigated in the post-Newtonian community also, because of course your point is that when you are doing this computation, even in post-Newtonian, your waveform is oscillating, then slowly it goes towards the static limit, and that build up towards the static limit goes at this rate, in this rate. And now the point is this out and in, let me just tell you, because I should not have erased this, because E mu nu log n cap is of the form summation, remember this was the thing, summation over pairs of particles A not equal to B. But when we wrote the formula, you will remember that there was a pair of incoming and pair of outgoing separate in this formula, and so that the incoming pair will give you this in, and similarly outgoing pair is the out. So is that clear? Because I am not rewriting this formula. So Chetan, some long formula, but sorry.
I believe it exists.
Yeah. So then this is the I mean also related to Chetan's question that I mean when you look at it, actually I think it's conceivable clearly that the tail to the memory will be measured before the memory itself, because the tail to the memory is what builds towards the memory. So I think there was a comment by Sachin that yesterday that are these all formulas abstract or can we measure? But this is telling us that if you have sufficiently good detectors, if we would be able to measure memory in a detector, we would certainly be able to measure tail to the memory in the detector. So this is a concrete space-time interpretation of our event shapes, and you clearly see that these are completely boundary data, right? Everything is written in terms of u and the angle, and so.
Detection of memory isn't as simple as just measuring the displacement of the mirrors.
Yeah, long after wave has passed by, so that means, but that's a very that's a very sensitive thing, right? Because already there is so much noise, so already things are always tiny vibrating. So to separate out that from the permanent displacement, I think the sensitivity required is higher than even the advanced LIGO. So I don't know the scales, but because that depends on the mass of the black hole also. But that Fawata's paper has some estimates. Fawata has, by the way, review called Gravitational Wave Memory almost 15 years back, where he discusses all this from post-Newtonian, only from post-Newtonian for bound orbits. Okay. Yes. Yeah. So that's what I'm saying. That this one clearly will be. Whenever you, so if you look at the plots, also, sorry, I'm derailing a bit. I apologize. So whenever you look at the plot also of how the memory is done in Fawata's thing, right? It is always built up like this. Right, because you have a 1 by u which will first, it's like your e minus 1 mu nu is like really going at the rate 1 minus 1 by u. So that's the point, like when you measure this, but you will always first, from the LIGO, right, you will first measure this. So their theoretical modeling never comes without the tail, it always has a tail.
Sorry, what is the y-axis, what is the x-axis?
No, just the time and strength of the displacement thing. Okay, so now that at least I have convinced you that these event shapes are purely boundary data, and in terms of they are also sourced by stuff only on the boundary, because it doesn't care about what happens in the bulk. And so to understand their universality, we should first investigate the boundary structure properly. So now we are a little bit in the classical GR domain. So now I'm going to do a small discussion of what is called asymptotically flat spacetimes in d equal to 4. And contrary to many claims in the literature, there are actually quite a lot of subtleties in the 4 dimensions, which are really always tied to this presence of this log mode in the radiation. So I will try to bring those out. Yeah.
So asymptotic separation that you have is,
Yeah.
that is going to be just a function of G.
Yes. I mean, the
You know what the mass of the black hole is.
mass of the black hole and the initial black hole mass, initial and the final black hole mass. And if you have a lot of finite energy radiation coming out, that is in the part of the nonlinear memory. So the practical application of this formula is that post-Newtonian waveform will give you a mu, because it gives you finite energy radiation. So you use that inside this Christodoulov, this nonlinear effect formula, and so that becomes part of your data. So think of a mu as a part of your boundary data, which is like finite energy waves hitting the boundary, and particles momenta at minus infinity plus. This is all part of your boundary data, and that fixes your event shapes, both these event shapes. So that's the setup. Okay, so I'm just going to give you, so basically the point is, because we have, as Aninda and Chetan were discussing, we have 0 cosmological constant. We want to look at, I'm putting, okay. We want to look at solution of this equation. And now the point is that, let me make a first claim that if all the matter is concentrated, this is, I'm writing it qualitatively right now, concentrated in finite spatial region, then at large distances. I will explain what these distances mean from center of scattering. Our G mu nu should approach eta mu nu plus corrections. So this is a, if you want, this is a underlying assumption in all the discussion we are going to have, that even if you do scattering, as long as your matter is not spread out everywhere in space, then of course it's spread out in space-time, then at large distance in any coordinate system, because even if you change the coordinate system, infinite distance remains infinite. So in that sense, a large distance is not the larger you go, the ambiguity in defining distance decreases. So that large distances, the metric should have this form, which means naively all the correction should be whichever way we define R, which we will define, whatever your R definition is, it should fall off like this at large distances. So if this happens, then this is a physicist definition of asymptotically flat space-time. And it's physicist definition because these things are a bit vague. It's a coordinate dependent definition. So there is a coordinate invariant definition which was provided by Penrose, which I think I will discuss either end of today or tomorrow, which is in terms of components of the Wild tensor. So if you don't know, please ask me. Wild tensor is basically kind of a gauge invariant part of the gravitational field. And so if a Wild tensor, Penrose showed that if a Wild tensor falls off, different components of Wild tensor fall off at some particular rate, then that is what would qualify as an asymptotically flat space-time. And this, I will write it a little bit because it will be important into how in 4 dimensions actually that Penrose's criteria is violated, which is now people are beginning to understand properly. So let me first write schematically what the criteria is. So there are these 5 scalar quantities, psi 0, psi 1 to psi 4. These are complex scalars, so they are together 10 real scalars, and they correspond to 10 components intuitively of the Wild tensor. So everyone knows the Wild tensor, right? Okay. So the statement of Penrose was that each of the psi k, the coordinate independent definition of asymptotically flat spacetime is that psi k should fall off as order r to the 5 k minus 5. So this was his criteria, that if you take psi 0, it should fall off very fast, psi 1 should fall off, and psi 4 should fall off the slowest, and it should fall off as 1 by.
But why do you say it's coordinate independent? There is R there, right?
No, the coordinate, yeah. So this is this. Sorry, I should say, yeah. So coordinate independent means these scalars are gauge invariant because they are Wild scalars. Of course, R is we always have to define some coordinate, but whatever coordinate you choose, because these are covariant quantities, like this fall off condition will not change. Yeah, so I will explain what psi k is. So there are there are these so okay, let me start. So that's this we can decompose our Riemann into the Ricci tensor, and so this is 10 components, this is 20 in 4 dimensions, so there are these 10 components which are which is called a Wild tensor, and this Wild tensor satisfies divergence free condition because of the Bianchi. So it just satisfies. So these 10 components we can kind of combine into 5 complex scalars, and so I will explain in a minute what they are. So yeah.
So the statement is that this G mu nu condition, the order 1 over R thing, if you change R, the power might change, but
exactly.
on the other hand, the power won't change.
Won't change.
That's
yes.
the statement.
Exactly. Yeah. Thank you. Yes. So here, this is really, yeah. Here, you are absolutely right. Like here, we could rescale coordinates and things could change. It may look like the spacetime is not flat, but if you compute this and this is true, then it would be flat. So let me now explain to you what these psi's are, and this condition, as I will try to at least have time argue that that this condition is violated as soon as you have massive particle scattering in 4 dimensions. So this is a this is a result. So this by the way, this is called peeling property, because this different components of Weil tensor are peeling. The supposition is that different components of Weil tensor are peeling at a certain rate, and this peeling property is violated in a interesting way if you have massive sources. And this violation of peeling is due to Christodoulov around 20 years ago, which we will come to later, maybe in the today or tomorrow. But let me explain what the psi's are first. So in order to explain psi, I have to do, so it's useful that to introduce psi, I should first talk about the structure of the boundary of Minkowski spacetime. So once I explain that to you, then I will introduce psi. So the first thing is that intuitively our goal is now the following, that because this is our setup. So we want to understand what is the structure of this boundary, this, and this. We are not particularly bothered about understanding what is happening here, because we are already assuming that matter is not spread everywhere. So, our goal is to understand what is the structure of, what is the geometry of these boundaries, because that's where all this data that give us event shape is defined. So first we are going to do this for Minkowski. We are going to understand what these different boundaries are. So let's start with the eta, which is, so I really apologize to experts. And so the first thing to do, what am I drawing here? I am drawing a place where gravitational radiation is going, but gravitational radiation is massless particles. So first boundary I want to focus on is where any massless particle will either end or emerge from. Okay, so that is the boundary I want to first focus on, and that boundary can be obtained by in the following way, as you will see in a minute. So let's first do coordinate change from tr theta phi to let's say u r theta phi, and then you can immediately see that this eta can be written as of course in this metric I cannot take r to infinity, because then I don't get anything sensible. But what I can do is the following. So what is my interest? My interest is that I want to evaluate what happens at infinite distance. That's where the boundary is. So I want to understand how to take infinity limits of this metric, and that of course we can't do, we get garbage. But what we can do is the following, that let's first let's change a coordinate from r to, let me call it f, which is 1 by r. So f is a bad coordinate at the center of our spacetime, but it's a good coordinate at infinity. This is a usual thing we would do, right? And so then eta becomes minus du square minus 2 du df by f square plus d omega square by f square. So of course we didn't do anything deep, we changed r to f, so obviously at f equal to 0 this metric diverges, but this gives us a window into what this infinity actually means, because we could now consider, instead of looking at eta, we could look at, so this is my Minkowski spacetime M, and I'm interested in understanding its infinity. So what I now do is to look at a new spacetime, which is Minkowski union. I'm right now just indicating it as a label, it will be clear what we mean, this boundary. And the only way I could make sense of this is if the metric on M is not eta, because the eta metric diverges at the boundary. So on M we put a metric, we call it eta bar, which is f square times eta. So that metric is simply minus du square minus 2 du df plus d omega square. F square du square, yes, of course, yes. And now of course you see that now for eta bar we indeed can take f equal to 0, because if you take f equal to 0 this goes, and if you are at any f equal to constant, of course this term is gone, and so then the boundary which is f equal to 0 has this as the metric, right? So that means that this space is coordinatized by, so everything else here is coordinatized by r or equivalently f, but now we have a boundary which is coordinatized by only u theta phi, because f is constant, f is 0, and the metric on this boundary is just 0 du square plus d omega square.
So we previously had a Minkowski space without boundary.
Yes.
Now we have with boundary, but
Yes.
we're actually excluding the center, right?
No. We are not excluding center because we were only interested in looking at the large R. So our f coordinate is defined at only large R.
Only the
Right. So we can always do coordinate patches, right?
So yeah, looks like that this new eta mu is eta prime also can also give you inside the Penrose diagram, excluding except at the center.
No. So that's what I'm saying. That now if I look at this eta bar, which is f square eta, and I write the whole thing, and then the point is that if I'm away from f, if I'm at f equal to infinity, I just work with my r coordinate. So this metric is everywhere away from f equal to 0, f square eta. Right? That's all. So if you want, you just think that this is what we do usually in Couch space, right? We have different coordinates which we glue together like on a sphere. So I am using r coordinate at around the center and 1 by r coordinate around infinity. That's the point. So f is equal to 0 is the where I am going. So then the gradient along this, of course, if you move along this, df is 0 na, because df is only inside. Okay, so that gives us a notion of this boundary, and that boundary is called future null infinity because that's we are moving. The reason it is called future null infinity, so this boundary is called future null infinity, and it's denoted as cry plus. And the reason it's called future null infinity is because because we use the coordinate u equal to t minus r, and so if you think that if I take large r, how do I reach u equal to any point on this boundary? So this point is parameterized by u, and if I take large r, in what way I reach constant u? Of course I have to take large t at the same rate, so I'm going towards the future only. So that's why this is called future null infinity. Okay. Now we could do exactly same thing from the past if I want to understand this boundary, except that I will use the coordinates instead of t r theta phi, I go to the coordinates v r theta phi. And I won't bore you now with more details, but you do the same thing, then you get the metric, as you could easily convince yourself, is again 0 dv square, where v is t plus r plus d omega square. And here the metric, as we saw, is 0 du square plus d omega square. So now we understood two boundaries, and one should remember that both these boundaries are cylinders because we have the coordinates are u theta phi, and u goes from minus infinity to infinity because t goes from minus infinity to infinity, and so this is topologically a cylinder, and this one. And the way I have done it, we cannot glue them together because they are we just use different coordinates, and there are several proposals to glue them together. There is one also by Chetan where he's able to use, instead of tr or vr, u and v coordinates together, and he's able to show a space-time where there is a gluing of these two cylinders at a given point. But the reason we are not discussing that part is because for radiation that is not important. Otherwise we would have to worry about that compactification, that what is happening at u equal to minus infinity and v equal to plus infinity also. I mean, or retarded and advanced. U is retarded and v is advanced, or outgoing and incoming null coordinates. Yes. Okay. So far we have these boundaries, and you may be for students. I mean, you may think why we have drawn two, because just to make explicit that we have a sphere at a. So that's the picture. This is our u coordinate, and at h fix u we have a two-dimensional sphere. Similarly for the v. And now we want to understand these boundaries, which are the future and past time infinity. But by the way, is there any question about this so far? So right now we are not looking at gravitational field at all. We just look at Minkowski, and we told we are just looking at its boundaries, right? So. Okay, so let me just first now tell you for Minkowski, how do we analyze the time boundaries, the future and past time boundaries. And now suppose we want to, so let's say we want to look at intuitively, this is t equal to plus infinity. Right, so it's parameterized intuitively by r theta phi. Right, so just to remind you, this is eta is again our usual. Now, if you want to only look at, if you only want to go inside at t equal to infinity, we want to only stay inside the light cone because we are not interested in going at large distances. So, a very good coordinate system to analyze this boundary of Minkowski spacetime is the following. So, now I am going to introduce. So, for null, for analyzing this boundary, we went from tr theta phi to ur theta phi. Now, we are going from tr theta phi. You will see in a minute why. I mean, it all looks like coordinate change, random coordinate change, but it helps us understanding some limits. So we go to what is called hyperbolic coordinates, which is defined as follows. So tau is and theta phi remain theta phi. So clearly you see that this coordinate is only well defined if first we fix the origin of Minkowski at 0 and then we draw the light cone and we stay inside the light cone. Only then this coordinate is well defined. Like we could say in this light cone or in this light cone, future or past, in both it is well defined. But we cannot, it is not a coordinate system which is defined here, which is analogous to your question about the f coordinate system at r equal to 0. But here the domain of validity is even smaller. It's just it's just this. And now, okay, if you do this and you write your metric in these new coordinates, then you see that this metric is given by minus d tau square plus I may forget, sorry about this. No, sorry. So just writing the Minkowski metric, we get this this as the metric eta written in these coordinates. Now you can do the same thing we did earlier. I will not bore you with the algebra. You define tau is equal to 1 by f. You rewrite this thing in terms of f, and you again do this compactification. You again rescale your metric with f square. When you do that thing, then the new. So please ask if I am talking garbage. So when you do that thing, you will get a new space-time. Let me call it m prime, which is m Minkowski plus the t equal to plus infinity boundary. Where this boundary is now coordinatized by rho theta phi, and the metric on this boundary is just this. So you see the qualitative difference in when we went to this boundary, the metric became 0 du square plus d omega square. So it's what we call degenerate metric. It has 0 plus plus signature. Whereas here the boundary becomes just our Euclidean metric. It's a curved metric, but it's Euclidean. It's a plus 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 signature. So of course you could have also taken t going to minus infinity and absolutely nothing will change because everything is coming with a tau square, right? So we have now defined two more boundaries. So now I'm going to draw it in once again. So my full space time is m Minkowski plus the union scri plus, union scri minus, union I plus, union I minus, where scri plus is the future null infinity, which is parameterized by u theta phi, and scri minus is also v theta phi, and I plus is parameterized by rho theta phi, and the metric on I plus is this metric. Okay, this metric.
Topology of I plus?
Yeah, the topology is because R is a radial coordinate, so topology is it's S2 cross R topologically, and the metric is what we call this Euclidean ADS, anti-de Sitter metric in 3 dimensions. So I plus is also it's not a, it's a half, I mean it's S2 cross R plus, and similarly I minus, they are both same. Okay, so now we have full glorified boundary structure. So I hope, is there any question about this? So this is all the boundaries of Minkowski that we have attached from outside. Okay, and now, Ainda, can I take, I have taken 5 minutes, right? 12:25. Okay. Now once we have these boundaries, we can define space-times which are such that they all share the same boundary, but inside they can have gravitational field. So I hope that's another way to look at asymptotically flat space-time. So now I'll give you a workable definition of asymptotically flat space-time, which is that so okay, now I'm giving you a slightly alternate definition, but that is equivalent to the Penrose's definition, which is the following: that consider any metric, consider G mu nu, which is a solution to Einstein's equation, solution to equations of motion, not necessarily Einstein's equation, but except that so it can have higher derivative terms, but it cannot have cosmological constant. That's the only criteria. So consider solution to equations of motion of gravity with lambda equal to 0. Then we call this G mu nu asymptotically flat if I'll write it first in words and then explain. If it has if its null infinity is scri plus union scri minus with coordinates u theta phi and v theta phi and metric 0 du square plus d omega square, and similarly for this one. So the intuitive idea is the following, and notice I am not talking about I plus I minus. The reason simply being that if you have matter particles, they actually hit time like in time. So Minkowski is empty. So Minkowski, nothing is happening on this space also, but because no matter is actually, because we are saying matter is always located in a finite spatial region, the matter is not spread out to infinity. So that is why the definition of asymptotically flat spacetime is such that its null boundaries are same as that of Minkowski spacetime. Okay, so that's an alternate way to define asymptotically flat geometry. So that is, we start with any G mu nu. Okay, so let me explain why I call it a workable definition, because you start with G mu nu, and suppose we say that we write it in terms of u r theta phi. That we can always do some solution to Einstein's equation. You do the same procedure. You take r equal to 1 by f and you consider f square G mu nu, and now you take the limit f going to 0. If this is exactly 0 du square plus d omega square, then we will call this spacetime asymptotically flat in the future. Okay, so I hope this point is okay. And similarly, if this with a VR, if this also is satisfied in the past, then we call it asymptotically flat in the past, and together it's asymptotically flat. So spacetime is asymptotically flat in the future and in the past. Okay, and that's our object of interest for understanding these event shapes. So is there any question about this?
Under this definition, any rescaling of determining y factor is depends on theta by w.
Yes, that's a very good point. So of course you are right that this f is not unique, right? Because we are that's exactly your point, right? You are saying that why did I, instead of, so I define it like this, but I could have looked at some f prime by f where f prime only depends on theta phi, right? Absolutely, that is correct. But the point is that if this will also go to 0 as f goes to, if f goes to 0, then f by f prime will also go to 0, because f prime doesn't depend on r. So the boundary won't change, right? The boundary metric will still remain this. So that's exactly the point, that we want to be agnostic about details of f also in some sense. I just for simplicity chose as 1 by r, but you could have chosen anything like this, for example.
You think that the boundary is conformally equivalent to this?
Yeah, but yeah, you're right, absolutely.
That will take care of this.
Yeah, but I just don't want to use the conformal. I mean because Yeah, you are right. I mean, I'm just saying that I was avoiding the word conformally equivalent because, yeah.
Little like plus or minus won't play a role because we are dealing with massless particles.
No. I'm saying if you have massive particles, they will go and hit I plus, right? So they are never empty in that sense, right? So what is only hitting null infinity is gravitational field. But because the gravitational field is die down at null infinity, at infinite distance, it's flat. But even if you wait for long enough time, particles always go. So once you have massive particles, I plus is never same as I plus of Minkowski. That's the intuition as to why we define asymptotic flatness only based on null infinities and do not include. Of course, you could say that I will also include in this spatial infinity that Chetan looks at, but I'm just for convenience, lack of time, not talking about spatial infinity. So there could be a more rigorous definition that I have asymptotically flat spacetime which has chi plus, chi minus and like a boundary at spatial infinity. That's a more refined definition, and it is not true that if it's asymptotically flat at null infinity, it is necessarily flat at spatial infinity. So that's that is an additional physical criteria, but I'm just avoiding it right now because in our scattering process, because nothing is happening at large distance, those criteria are satisfied. Okay, so I will just now tell you, now with this workable definition we can actually write down what are all possible asymptotically flat geometries for satisfy Einstein's equation, and this was a work of Bondi. So once we have this idea that null infinity should not change from Minkowski, what Bondi showed is the following. I think in 60s, that all solutions to gravitational equation of motion can be parameterized as follows, and I'll parenthesize this, if we are close to chi plus. So if you are studying your geometry close to future null infinity, then any solution of theory equations of motion, Einstein theory plus higher derivative theory, all the solutions can be parameterized like this. So I will first write and then explain. So let me explain the notation. So as you would know that if you want to solve Einstein's equations of motion of gravity, you have to fix a coordinate system. So we have already, what Bondi does is, he says that, well, I'm fixing my coordinate system in such a way that my radial component of the metric is 0 and my GRA components are 0. I need 4 conditions to fix 4 coordinates, right? So I'm giving you 4 conditions, that the radial component is 0, these two, gr theta, gr phi are 0, and the you see that here I have written gamma ab as a function of r u theta phi, and I have just scaled out r square. The reason is the following, that the final condition is the determinant of gamma ab should be same as determinant of okay, let me write and then explain. Metric on the sphere at infinity, but I will explain what I mean. What I mean by this is the following, that take this guy, gamma ab, and the spacetime will be asymptotically flat if the expansion of gamma has the following form. This is I'm just writing first few terms, and now the point is that if all these other terms are trace free, then that would imply that determinant of this full metric is same as determinant of Q. So that's the 4th condition. So remember, we need 4 conditions to fix 4 coordinates, and these are 4 conditions Bondi provided. And in this coordinate system, he showed that if any solution to Einstein's equation with massive sources or anything close to future null infinity has I missed some term. Sorry. of course there are other terms, right? So I apologize, plus because GUA is not 0, so it should of course be there. I just missed it. Where this V, so all of these are functions of UR theta phi. All the components that I have written. But of course, for them to be Minkowski at large distance, they must be satisfying some fall off. And then Bondi showed what fall off they have to satisfy. So for example, V is given by, okay, I will just write it, minus, okay, I will write in a minute. I will explain in a minute what I mean by this. So this all came from equations of motion. He looked at Einstein's equation at large distance and deduced all these fall off conditions on different coefficients. Okay, so the point is that this RQ is the Ricci scalar of this metric. This metric, it should be by 2. So if you have a unit sphere metric, then this coefficient is just 1. And you see that if you now take R here and divide by R here, and you expand this coefficient here, then you will get, first coefficient is 1, which is minus du square. So you already see that this component matches Minkowski as you do 1 by R expansion. Similarly, you immediately see that because beta is falling off like this, if you do an expansion of this, you get 2 ddr as the leading component, and you know that's the logic. So this is the full parameterization of asymptotically flat spacetimes close to future null infinity. Okay, so any solution Einstein's equation must look like this in this coordinate system. Okay, so now that we have a control on this, tomorrow we will see that given this, what are the symmetries that these spacetimes inherit? Because one group of symmetries we know, because the spacetime is Minkowski at large distance, it's Poincare, but we will see that this has a much richer symmetry structure, and those conservation laws will give us these event shapes that we talked about. So sorry, I didn't, I'm lagging behind, but yeah, thanks.
See you after that.
Yeah. Yeah, exactly, similar.
Once we reach the law,
Yeah.
we can't continue the expansion. This is related to the trace anomaly in the ADX.
Yes, exactly.
Here, does the expansion break down also after you reach the log, or?
No, it doesn't break down in the sense that you will have subleading terms with higher logs, etc. also.
But you have to provide some additional data, I guess.
That's an interesting point. So this E will be exactly, I will tell you more. So for example, this first log component, which is this guy, this will be 0 if you have no massive sources. So these are all fixed. So this is the point. And if you have this, then this Penrose's peeling breaks down. So the point is that these are sourced by masses. So if you have pure gravity, then these coefficients are not there. And Penrose was really analyzing pure gravity, and that's why he didn't care about these terms. I must say that there is a lot of debate about this even after Christodoulou's result, because many mathematical relativists like Ashtekar, for example, they have spent their life examining asymmetrical flat geometries, assuming that peeling is preserved. And so there is a disagreement among a section of mathematical GR community that Christodoulou's result is not valid. Like there must be peeling, and these terms must somehow be gauge or something, log terms. But what is remarkable is that our results of event shape are completely insensitive to the fate of the peeling, like whether peeling is there or not. So Anida, I don't think I will finish the quantum, but that's fine, right? I mean, or I don't know.
I mean, when are you leaving?
No, I'll leave on Sunday.